Hi, I'm Peter Haddock and I'm here at Perkins Engines in Peterborough with Graham Hill, who's a structural engineering manager. Graham.
Hello.
When we talk about structural engineering, we think about big buildings, but when we're talking about engines, obviously there is a structure involved in every engine that you manufacture and the parts that actually go into it. So tell me a little bit about yourself and the role that you do here and why it's so important.
Well, our job is fundamentally to make sure that our engines are structurally sound, that they are durable for the life of the product, and they also deliver the performance and the cost that the customer expects us to deliver.
So what I've been doing recently, folks, in my Discovering the Power of Perkins series, which this is a part of, is going around the factory here, all the development phases and everything like that. However, until now, I haven't come and talked about how you can actually simulate the engine before it goes into that production process. So simulation is a really important part of that initial phase of when you're going to design a new engine, isn't it?
Yeah, it enables us to learn an awful lot about the product before we've even started making it, and it enables us to make really intelligent design choices early on in the process.
So when we talk about simulation, lots of people have gone on simulators to see how the diggers that some of your engines are going to are operated and things like that. What we're talking about is all the different elements that come together, isn't it? So talking about how they perform together to give that ultimate power and efficiency that comes through. So what's the process that you go through then when we've got a new engine to deliver like the ones you're delivering stage 5 now?
So we start really quite simply. We can start with reasonably simple mathematics, the sort of stuff you do on a pencil and paper, simply to get some of the key dimensions right. But you soon realise that those tools are quite limited, and then you can start to use the power of computing and software to get you more detailed answers to the questions you're posing. And so what we will use a simulation to do is to drive the fundamental dimensions of the product from the heart outwards. So right at the core of every engine is the crankshaft. So if you get the fundamental crankshaft dimensions right, you've built in a degree of robustness, a degree of efficiency, and also you've driven the size of the engine physically so it can fit into a space, and you've got that in right at the beginning, right at the heart.
And I think that's what's really interesting for me, because we say the heart of every machine is its engine, is the power that goes into the performance of that machine or that item. And then we're talking about the crank being that heart of the heart. And so we're now seeing, Graham, a lot of changes in the industry where we're demanding smaller engines, but having the power, not just to meet the needs of the wheels that go round or the tracks that go round, but also this much higher demand for hydraulic power, as well as we look at attachments and things like that go onto machines, whilst also saying we need to save fuel and reduce emissions.
That's
and we've
exactly
got
right.
all of those things on together. So when we're talking about the way in which you have reduced engine sizes recently, but have kept and maintained that power so that actually they can perform better than the larger sisters and brothers that were gone previously. It all starts with that crank, and then what actually happens then when you simulate things, and how does that build out from that heart?
We aim to get the key dimensions of the crank, and as you're driving more power through the engine, the crankshaft has to get stronger, which can in turn mean you're generating more drag in the bearings. So we're constantly aiming to get the balance right between having a strong, robust crank with big bearings, but also getting the size of the bearings right, such that you're not wasting too much fuel just turning the bearings round. But also, when we've built the models of the crankshaft, we're putting the loads from the pistons through the con rods into the crank. That load gets returned to the engine, so we're then able to use that to see how the components attached to the engine respond to the excitation, and make sure in turn that they're really durable. So our analyses, they can go from the simplest component and simply look at that part and how it behaves in isolation, to how a whole collection, to a total engine assembly, responds and behaves a full system. So you've got a really broad spectrum of work that we can do.
I think what's interesting for me with this, folks, is I've just been in my visits in the Power of Perkins series in the cold chamber. So we all know that your engines have to work in really, really cold temperatures.
Challenging conditions.
We also know that there's a noise element that people want to reduce in the overall noise of engines. So you've got a noise chamber here.
Yeah.
We also know that there are extended life from the maintenance perspective of your engines, that you've added hundreds of hours before people have to maintain them because of the work you're doing. This is why the simulation is so important, folks, because also now we're able to change the way with the smaller engines and put them into different applications that we weren't be able to do before. So again, all of those things have to be simulated within your team, because folks, Graham and his team take the stresses out of the whole situation. Stressful designing, everything like that, but using machinery and things. But what we're talking about is the stresses between the components like this. That is a fundamental, isn't it? You were talking about pistons and piston rings and things like that with me before. Explain how you're taking the stresses out without, taking the power out as such.
So in one way, you mentioned the noise team, and what we can do is we can take the loads that each cylinder puts through the engine as it fires, and we can see how that force is then transmitted more widely to the attached components from which the noise comes. Or we can look at the engine block and put extra ribbing in where you need to put the ribbing in, so that it's not behaving like a loudspeaker as it vibrates. And fundamentally we can make sure, as you say, that the stresses going through the crankshaft that's delivering that load aren't enough to cause the material in the crank any damage in the life of the engine. So it's all fundamental about understanding, keeping that stress level under control such that the product is successful for the life that the customer expects.
And one of the things that I thought was really interesting is how you then go and take that to your component manufacturers, as well, because there's lots of other people that come into play that you work with as a business to actually create the overall engine. And so when you're working with the sort of pistons, when you're working with the rings, when you're working with the rubber sort of, dampeners and things like that, all of that has to change when you've got a new engine. But all of that sort of process and the development at the start says to your supply chain, here's what we're looking at. Can you go away and look at that as we build through that process? So as the simulation has gone through, therefore we get to a point, Graham, where you're quite happy with it. And
that's the idea.
And so we've done all these things, we've done all the pressure testing, we've taken some of the stresses out, and then it goes to the building of the engine, folks, in the whole development centre we've got behind us here, and then onto the line. But your role doesn't stop at that simulation piece. You've done it at the start. And what you've developed is software solutions over the years since you started with the first ever computers, pioneers here, and developed your own, not AI, I'd call it artificial intelligence software things, but what about PI, Perkins Intelligence, that's gone into your own software making? That is all taken through the whole process, isn't it? You're using software and analysis that can tell us what's happening, simulate it, but also that can analyse performance as we go through the journey, isn't it?
Absolutely, yeah. So way back we would have been using simple calculations to develop the engines, but they have their limitations. We soon realised that computing offered us the ability to do more and better calculations to capture more of the physics that's going on inside an engine. So we developed our own codes because commercial codes weren't available. And we still continue to have our own code and develop it, because although there are now commercial software tools available to help us, we still believe we get a competitive advantage from working on our own. And it just enables our products to have that little edge over our competitors, because we can probably build in that extra degree of durability or compactness or performance that just gives you that edge in the marketplace and when you're using the product. And you can use these tools in a number of degrees. You might be tempted to put so much physics in
Yeah.
and it takes so long to solve and is so complicated to build that actually you're looking for a really quite simple answer. So there are times when the answers based on almost pencil and paper calculations are adequate and appropriate, and you use those because they get you there quickly. But there are also times when you realise that just doesn't tell you what you need to know, and then you have to build the layers of detail into the modelling and accept the fact it's going to take you longer to build and solve the model because the answer you need requires all of that extra work.
And what's really interesting, folks, is when you take apart an engine in simulation, you're simulating it using this high level of computer power, and you can actually do things that you can't measure when you are actually putting that in the engine bay testing areas that they do here at Perkins as well, because you can take out the components and put them back in again with different seals and things like that, can't you?
That's right.
This is great.
Yeah. We can make physical measurements that you can't make in a running engine. If you were to look at how the shape of the cylinder bores varies as the engine warms up and cools down, we can confirm how it is when it's cold when you first assemble it. Our simulations and physical measurement will align, and then we can warm the engine up. But you can't take those measurements in reality because pistons are going up and down and getting in the way. So we can then tell what's happening inside the engine to a far greater degree than you can physically measure.
And that in itself then helps the overall development to the perfect end goal, which obviously you've then got your colleagues testing in here, you've got your zero line where you're testing the manufacturing and everything, and then you've got the real world scenarios where customers are coming to you and saying, we want to fit this engine in this particular machine in this particular way, and all of that element comes to play, doesn't it?
Absolutely. So we can take those parts of an engine that are unique to a particular customer, and we can assess how they behave and perform before we've built the engine. And the idea then is that you've done the simulation, you're confident it's going to work, and you can do one test simply to confirm it before you then go away and make the engine in quantity.
So folks, it's all about simulation, it's all about the latest technology. We call it AI in the outside world. I'm going to call it PI here, Perkins Intelligence, as the team have worked through all of the processes from the very first computers, pioneers, right way to technology and things that we see in the screens behind us. Graham, it's fascinating to see how you make an engine before you make an engine.
Absolutely.
Great to talk to you today, and I'm sure we'll be back to understand a little bit more about how all of that process delivers into the end result, which is fundamentally lots of engines coming out of the factory here at Perkins, going all around the world to power all sorts of fantastic equipment. Cheers, great to see you.
Thank you very much.